Good morning, everyone. Today we want to present to you all about fatigue tests for subject material science. Before I begin the topic of fatigue testing, let us first take a moment to understand what fatigue actually is. So, what is metal fatigue? Metal fatigue is caused by repeated cycling of the load. It is a progressive localized damage due to fluctuating stresses and strains on the material. Metal fatigue cracks initiate and propagate in regions where the strain is most severe. The process of fatigue consists of three stages. First, initial crack initiation. 2. Progressive crack growth across the path. 3. Final sudden fracture of the remaining cross section. With this fatigue graph, we can understand that fatigue limit is the largest value of fluctuating stress that will not cause failure for essentially an infinite number of cycles. Fatigue limit, also called as endurance limit. Fatigue limit for many steels between 35 until 60% of tensile strength. Aluminium does not have an endurance limit because of its material structure and dislocation behavior under cyclic loading. So, why the aluminum lacks an endurance limit? First, we should know about the microstructural behavior. Aluminum has a face-centered cubic crystal structure which allows for easy movement of dislocation. For too easy, we understand is an imperfection in the atomic lattice. This makes aluminum more prone to damage accumulation even under low stress. The second factor why the aluminum does not have an endurance limit is because no plateau on SN curve. Unlike steel, aluminum SN curve never flatten out, meaning fatigue damage continues to accumulate at any stress level. Eventually, a crack will form and grow, even under low cyclic stress. The third factor is surface and oxide effect. Aluminum naturally forms an oxide layer which can influence crack initiation and growth. However, this layer doesn't have not prevent fatigue failure at low stress. So, the fatigue life, number of cycles to cause failure at specified stress level. Fatigue strength is the stress level at which failure will occur for some specified number of cycles. Example, 10 mega. Fatigue strength is the ability to take a repeated loading. Now is the time for us to understand about fatigue tests. Fatigue testing is a method used to evaluate the durability and structural integrity of material under cyclic loading conditions. Fatigue tests also to determine how material behave when subjected to repeated stress over time, which is crucial for predicting their lifespan in real-world application. Fatigue failure occurs even when the stress levels are below the material ultimate tensile strength, making this test essential for safety and reliability in engineering. And for this slide, we already put the link demonstration video from YouTube for every type and method on fatigue test. So we from group E hope you all can understand how the fatigue test work from the link given. So for now, I just only explain to you all about the principle, application, advantages, and disadvantages only. So let's begin with the first point of type and testing method for fatigue tests. The first point describe the rotating beam fatigue test, a widely used method where a specimen is rotated under constant bending load. This test is primarily applied to metal and alloy to evaluate their fatigue behavior. One of its key advantages is its simple setup and cost effectiveness, making it particularly suitable for high cycle fatigue testing. However, the notable limitation is that it only assesses bending stress, excluding other stress type that materials may encounter in real-world application. The second point, expand the axial fatigue test, also known as the tension compression test. In this method, a specimen undergoes repeated cycles of tensile and compressive force. This test is particularly valuable for evaluating components in aerospace and automotive industry, where materials experience similar real-world loading conditions. Its primary advantage is the ability to accurately simulate actual service stresses, providing highly relevant fatigue data. However, the test requires extreme precise specimen alignment to prevent buckling, which can complicate the setup process and potentially compromise test result. The third point, discuss the flexural fatigue test, also known as the bending fatigue test. In this method, a specimen undergoes cyclic bending loads, typically using a 3-point or 4-point bending setup. This test is commonly applied to materials like polymers, composite, and concrete. A key advantage is its suitability for brittle materials, which may not perform well under tensile fatigue tests. However, the notable drawback is the stress concentration at the loading points, which can lead to premature failure and affect test accuracy. The fourth point covers the torsional fatigue test, where the specimen is subjected to cyclic twisting force, inducing shear stress. This test is particularly useful for evaluating components like shaft, springs, and gears, which experience torsional loads in real-world application. A key advantage of this method is its ability to assess shear fatigue resistance, a critical property for rotating or twisting components. However, the test setup tends to be more complex compared to other fatigue testing methods, which can increase preparation time and costs. So, for the fifth point, covers the thermal fatigue test, where a specimen is subjected to repeated cycles of heating and cooling to generate thermal stresses. This method is critically important for evaluating components like turbine blades and exhaust system that experience extreme temperature fluctuating during operation. Its key advantage lies in the ability to accurately replicate real-world thermal cycling conditions, providing vital data on material behavior under thermal stress. However, this test requires specialized, often expensive equipment capable of precise temperature control, which can limit its accessibility for some testing scenario. The sixth point, introduced the ultrasonic fatigue test, also known as VHCF. That stands for Very High Cycle Fatigue Testing. This advanced method utilizes high-frequency vibration at 20 kHz to dramatically accelerate the fatigue process. It's particularly valuable for assessing medical implants and microelectronics that must endure extreme longevity. The primary advantage is its unmatched speed, capable of completing millions of test cycles in just hours, compared to weeks with conventional methods. However, this technique comes with significant limitations. It requires substantial investment in specialized equipment and can only accommodate very small specimen size, which may not fully represent actually component behavior.
For this slide, we're going to talk about the importance of fatigue testing cannot be overstated as it serves four critical functions. First, it ensures the safety and reliability of engineering components, prevent catastrophic failure. Second, it enables engineers to predict material failure before it occurs through rigorous simulation of service conditions. Third, testing significantly reduces long-term maintenance caused by facility optimal material selection during the design phase. Finally, it serves as an essential requirement for regulatory compliance, particularly in safety-critical industries like aerospace, automotive, and medical device manufacturing, where material failure could have several consequences. Challenges. Conducting effect fatigue testing present three major challenges. First, accurately predict real-world condition remains difficult due to the complex variable nature of operation environment. Second, testing composite material is particularly challenging as their anisotropic properties and complex failure modes require specialized approach. Third, research face significant cost constraint while scaling up tests to match actual component size or testing volume. Additionally, environmental factor is temperature fluctuation and corrosion effect must be careful, controlled and replicated as they dramatically influence material performance but are often difficult to simulate in laboratory settings. So for the conclusion, fatigue testing serves as a critical tool in engineering, enabling the assessment of material durability under cyclic loads and ensuring the safety, reliability and cost efficiency of components. Despite the challenge such as replicating real-world conditions, testing complex material and managing costs. The evaluation provides invaluable data to predict failure, optimize design, and comply with industry standards. So that's all for today, and thank you for having our time today.